Hi, this is Cameron, and I'm going to be doing a review on the concept of partial derivatives. So, a partial derivative is when we take the derivative of one variable in a multivariable function and treat the others as a constant. Let's show you an example. So, in this function here, which is f of x and y equals 2x squared y, we want to take the partial derivative with respect to x, which means we are taking the derivative of x and treating y as a constant. So the partial derivative with respect to x is 4xy. The derivative of x is taken normally, and y is treated as a constant and left right there. Let's do another example. So we have a new equation, which is f of xy equals 2x squared plus y, and we want to take the partial derivative this time with respect to y. Notice the difference in notation there where it's f subscript y of xy. And in this case, the derivative is 1. That's because 2x squared is treated as a constant, right? Because it is a different variable than the one we're taking a partial derivative of. So it's treated as a constant, and the derivative of a constant is 0, and the derivative of y is 1. So the partial derivative with respect to y of 2x squared plus y equals 1. Now, the same thing applies when there's three variables. When taking the partial derivative, take the derivative of the variable that we're talking about and treat the others as a constant. Let's do an example. The function here is f of xyz equals 3x squared yz plus 2z squared plus 6x. Let's take the partial derivative with respect to z. In this case, we get 3x squared y plus 4z. Notice that 6x, that term is just gone. And that's because 6x is treated as a constant, and the derivative of a constant is 0. Now let's talk about the concept of higher derivatives. So, in a multivariable function, we can take more than one partial derivative. This means that, for example, we can take the partial derivative of a function with respect to x and get a result, and then from that result, take the partial derivative of the first partial derivative again with respect to x, and that would be the second partial derivative of x, and that would be denoted as f subscript x. That's just one example. We can do it a little bit differently too. We can take the first partial derivative with respect to x, and then from our result, take the partial derivative of that function with respect to y. And that would be denoted as f subscript x subscript y. Now, f subscript x first means that the first partial derivative we're taking is with respect to x, and y being second means the next partial derivative we're taking is with respect to y. And I'm going to show you an example of one of those right now. To demonstrate the concept of higher derivatives, we're going to use this two-variable function here. It didn't come from anywhere, I just created it, and it works well to show what I'm talking about. So the function is this: f of xy equals 2xy squared plus 4x squared y cubed. To find higher derivatives, the first thing that we have to do is take the first partial derivative. Now, we're going to take the first partial derivative with respect to x and with respect to y. There are two different equations that we get. There are the first partial derivatives. The first partial derivative with respect to x is on the left. The first partial derivative with respect to y is on the right. You can see that there are two different results denoted with two different notations. Okay, now let's take the second partial derivative, and there'll be four results because of each of the two first partial derivatives, we're taking the second partial derivative with respect to each variable from the first partial. There they all are. So on the furthest to the left is the second partial derivative with respect to x both times. And the second from the left is the second partial derivative with respect to y of the first partial derivative with respect to x. And you can see that in the notation where it goes x first and then y to denote that we take the first partial derivative with respect to x first and then y second. And then we move along to the first partial derivative with respect to y and then taking the second partial derivative of each variable from there. And you'll notice that f of xy equals f of yx, which means that when we take the first partial derivative with respect to x, then the second with respect to y, that equals when we take the first partial derivative with respect to y, then the second with respect to x. And that will always be the case.